This video is about the 2-channel netafedri. First I will look at the noise floor and sensitivity. I have set minimum gain and now I step it up in the steps available here in Linrad. 1. You can see the noise floor goes up on the S meter, and then it goes down, and it goes up, and it goes down. And it's the same in both channels, blue and red on the screen here. Now I inject a signal into one of the channels. Here. And you can see, when I now step the gain down, every second gain level has a higher noise floor. Not very much, but a little bit. So it's more advantageous to use the ones with a low noise floor. I will change the scales a little bit. As you can see, the gain differs by about half a dB between the channels, and I now start to increase the gain, looking at the noise floor. And increasing the gain does not change the noise floor yet. Now there is a very small increase. And here the noise floor is degraded by 0.3 dB or something. That's a very small. So I increase again. And that's the highest gain. So the second highest gain, this is the most favorable gain setting for sensitivity. And it also gives very close to the full dynamic range, to within 0.3 dB or so. I have two generators here, each one connected to its own input on the afedri. They are locked to a common 10 MHz reference. Starting at minus 40 dBm, I will now step the level up until I see saturation. It's something like this. One would see this better with an intermodulation test. Here we read 27 dB on the S meter, but the generators show 26 dB, means we have the point of 1 dB compression. It is not saturation in the AD converter. If I increase gain here, you see what happens when the AD is saturated. So the level is now 1 dB below the point of 1 dB saturation, and that's minus 28 dBm, which is also properly shown on the S-meter graph. The fairly ugly spectrum we see here is because of the noise from the generators. They are not very perfect. I have now enabled correlation spectra. The yellow trace is 496 averages, and you can see that the noise in the average spectrum is much lower. That's because the noise from the two generators is uncorrelated. They are locked to a common 10 MHz reference, and spurs, like we have here, they are not removed by the correlation process, but the noise is. That is because the spurs are fixed in their phase relation to the 10 MHz reference. I have now connected a very good crystal oscillator and set it to the 1 dB below the compression point at minus 28 dBm, and the spectrum now looks far better than before. If I switch off the signal like this, you can see on the waterfall the noise changes very little. Here is the noise floor 20 kHz away. 20 kHz, as you can see here. And the level is minus 122. And I switch off the signal. And then we come back to the original value, minus 123. So it means the noise figure degrades by 1 dB only at a frequency separation of 20 kHz. And if I go to a wider separation, let's say 100 kHz, it must be somewhere around there, and enable the oscillator, you see, it's running, but there was no difference on the noise floor. The noise floor at 100 kHz separation is, as we have seen, minus 123. That is 95 decibels below the reference carrier at minus 28. So it means we have 95 dB in 10 kHz, or minus 135 dBc per hertz for the white curve you can see here. And I start the correlation from scratch again, and you can see here 16 dB, and I can move a little bit in frequency in case there would be a spur on this particular frequency. No. So the green curve is about 15 decibels below. That's the limit of how sensitive we can use this dual ephedry to measure sideband noise of oscillators. We can look down to 35 plus 15. That is minus 150 decibels. So this instrument can see sideband noise as well as a Perseus or some other high-class receiver by this trick of using the correlation. There was a glitch. That's not so pleasant, but it doesn't happen often. I have now turned down the gain to 23 dB and calibrated the S-meter to show 16 dBm. That's the level I'm sending into the ephedry right now. The noise floor then is minus 112. 112 minus 16, that's 96. Very similar to before. I have now switched to the good oscillator and set the level to show minus 16 dBm on the S-meter. Have a look at the green track here. We can clearly see that it's about 5 decibels stronger here than it is here. So it has some close range sideband noise. That's the sideband noise of the local oscillator at 80 megahertz. This unit is modified with a capacitor across that oscillator. It was needed in the particular box we have. I don't know whether it is useful on other units. It might be easier to see when displaying a narrower frequency range like this.